One. Okay. So can everyone hear me? Okay. Okay. Sounds good. So today, I'm going to introduce the graph databases using Cypher Query language and Neo4j, a very popular graph database offering nowadays in the market. So the first thing is let's talk about a little bit on the history. So in the history, there are lots of logic data models have been proposed. So even though nowadays in a database lecture we are study relational model, but that's really not the only one appears in the history. So start with the very first data model is called hierarchical, which is first proposed by IBM product called IMS. And then there's another very popular data model called network, which is proposed by a group called Codacell. And now this we are studying relational. There are many extra. So the history lesson we learn from those different data models in the history is that it's really what goes around comes around. So graph databases use data models that are really spiritual successors of network data models that is very popular in the 1970s. And by the way, the COSL is a short for a committee on data system languages. The following is really showing a data model a data that's modeled after network data model that has a supplier, supply, and a part. And you will see later on that this network model shares great similarity with what we are going to talk in greater details about property graph data model. So in the landscape of graph data models, there are really two major classes. The first class is called edge-labeled graph. In this case, we assign labels to edges that indicate the different types of relationships between nodes. For example, suppose in the below we have this three nodes, a very simple graph that's trying to model to a person and one TV show called The Office. So we have Steve Carell and The Office and BJ Novak. They are all nodes. And we have three edges. One, we have edges called X in. It has a label X in that goes from Steve Carell to The Office. And we have the other two edges that goes from BJ Novak that goes to The Office. One is called X in, which try to model that BJ Novak play a role in the Office TV show. And another edge is called produces. We try to model that BJ Novak also serves as a producer for the TV show. As we can see that any edge in this model has three components. One is called Steve Carell. That is the node where this edge goes out. And the middle part we have X in, which is the edge label. And the third component is the office, which is the edge goes in. So since we have this edge has three parts, sometimes we call this whatever the database is that uses this kind of like a graph model called we call them a triple store. And this edge label graph, which is the basis of a resources description framework called RDF. The second kind of graph model that's actually Neo4j uses is called the property graph model. This model which extends the edge-labeled graph with labels, so both edges and the nodes can be labeled with a set of property value pairs that's called attributes directly attached to each edge or node. So here we have exactly the same data we saw last slide. So here we have, again, three nodes and we have three edges. But there are a lot more information going on here. So the node, for example, the node N1 that has a node label called person, it has two key value pairs. One is the name, Steve Carl, and the second is the gender, male. For another example, for the edge, they are pretty similar. We have edge that's E1 that has a label, edge label X in, and it has two attributes. So one is a row and Michael G. Scott, and the other is called ref Wikipedia. So one thing to note here is that we don't edge or a node doesn't really have to have attributes. For example, in this edge, that's E2 edge, we only have label produces. We don't really have any attribute for that edge. So what's the difference between the property graph and the edge label graph? So having node labels as part of the model can offer a more direct abstraction that is easier for user to query and understand. So in this example, we sort of understand that Steve Carl and BJ Novak actually are person's name, but in a more generic usage scenario that we may not be aware of what's the semantics of Steve Carl and BJ Novak means and what exactly it's trying to represent. So in this case, property graph has a better kind of like modeling power than the edge label graph. Another suitable scenario for a property graph is that it can use we can regularly add any new types of meta information to the node or edges. For example, in the previous slides, we see that we have two attributes for the person label. If we want to introduce another key value pair, that is very easy to do so. But for the edge label graph, that is very hard to do that. Even though it can, but that requires some extra care. So now, since we talk about relational model in the whole semester, so we want to kind of see what exactly try to model the same data in the relational model and to get a sense of what's the difference between graph database model and the relational database model. So here, in this case, we have 4 tables. And those tables, for instance, we have this first one, we have X in, that's trying to model this X in edge. And second, we have this person table that's trying to model this person node. And the second, we have this produces, which try to model another edge in our graph database model. And to make sure that each those edges are properly connected to the right nodes, we actually add lots of constraints using, like say in this case, we have 4 foreign key constraints to ensure that we make sure that each row in the table that connect to the right title ID. For instance, in this case, in the TV show table, this corresponds to the office. But one thing you can see here is that actually we introduce quite a few redundant information here, trying to basically ensure that each row in the table connect to the right entry in the other counterpart table. Another thing to notice is called this schema extensibility or link discovery. So suppose we have this one graph called TV show that connects with another node called year 2005, and we have another table that we have another like say table or graph. In this case, it doesn't really matter. That's called production company BBC and with exec producer Ricky Gravis. So in the graph, we want to kind of like trying to say, okay, if we want to say in this case, the initial data, we have these 2 distinct, you can say this kind of like 2 graphs that are not linked together. But what we want to say that we want to link the BBC, the production company, to this TV show. In the graph, it's pretty simple because we just simply add an edge that connects between these 2 nodes. However, if in the relational world, that requires a lot of effort because we want to alter the table, the TV show, with another column called production company, and we have to introduce basically a constraint that references another set of tables. In this case, the production company table. So that makes it very hard to modify schemas in the relational world compared compared to the graph database. So in summary, the public graph versus relational model, we have this graph structure actually is more intuitive than a collection of tables. What we will see in the homework, probably we see the org chart, and also we see that in the homework 4 we see that how we can model the graph using relational model. We kind of like there's a really ambiguity here, whether we are modeling a directly graph or a graph is directed edges or if the graph is undirected edges. So without looking at graph topology, we cannot tell by simply looking at the relational tables in the relational model. Another one is that, as we saw earlier in the slides, that we introduced lots of these different IDs to ensure that constraints are properly constructed for a relational model to model these edges connect between two nodes. That's really introduced lots of data storage from user perspective, like primary key and the foreign key. Another is that one thing is to notice that is that in the relational model, we cannot have two tables with the same name. So if we want to have, say, we have one table TV show, we have a title year, and we want to create another table called TV show title year production company, that's really not possible. Whereas in the graph database, we can just say both nodes will have the same label TV show, but one node will have a title year as its attributes, but the other node will have a title year production company as its attributes. Last but not least, actually we'll see later on that graph databases actually offer a quite nice query language to work with graph problems. So now let's start to introduce this Neo4j. So Neo4j is a graph database that uses public graph data model with a query language called Cypher, as suggested by the slide's title. Actually, in the graph database domain, there's really no standard query language yet. Many vendor-dependent flavors. We'll show, for instance, 3 examples here. So suppose we want to find the co-stars of the office. This is a language called SPARQL that is designed for querying whatever the data that's modeled using the edge labeled graph RDF. This green one, which we'll talk about in much details about its syntax and semantics, actually is using the Cypher syntax. Even in the public graph domain, that Cypher is really not the only one language to allow user to query the public graph data model. So this is another one called Gremlin that is also very popular in the market. Lots of database vendors actually support this one usage as well, that express the same query but using quite different syntax. So we talked about that there's really no standard query language yet, but so there's actually a standardization effort which is called trying to come up a query language called Graph Query Language, GQL, just like a SQL for the relational model. So this picture actually showing that what is the relative recent landscape of this query language in the graph databases. So we have quite a few players here. We have Neo4j. It has its own unique query language called Cypher, and it's open sourced to become Open Cypher. And Oracle, on the other hand, has its own query language that's designed for the graph database model called PGQL. And there's quite a few that come from academia research here, and also here on the right left corner, actually the right bottom corner, there's another database vendor called TigerGraph that it actually has its own query language called GSQL that really basically embed the graph query language capability inside the SQL language. And also there's called LDBC, called GCore, which they propose what exactly the ideal graph query language should look like, or what exactly the features it should contain. So different people have different opinions towards what's exactly the graph query language should like. So there's really no standard yet, but according to the timeline, there should be some news that in next year. So now let's actually take a closer look to how we can create our first property graph with Neo4j. So, here we're trying to create the office crew graph. It's exactly what we have seen a few times here. We have 3 nodes again and 3 edges. So here the syntax is quite simple. So here we have a create, which indicates we want to create a few nodes and edges. So we have n1, n2, n3. Those kind of like as a variable so that you can reference later on. For instance, once you want to, suppose we have this 3 nodes, n1, n2, n3, and we want to create edges that connect n1 with n2. So here we can directly reference n1. And I want to say that it has to connect to n3. So let's first take a look at the node here. So n1 as a variable, we have is a type. You can think about this as a type or type for that, or in some sense it's kind of like as a relation name in the relational model. So this one is a person as a label, and we have a few attributes here: name, Steve Carl, gender, male. And similarly for the n2 nodes, we do similar things. And for the n3, we have a new label called TV show that we have one key value pair here titled office. So next, we want to just create 3 edges here, which is n1 that has a label xin, and we can attach a few attributes here, and it connects to n3 and n2. Again, we have xin as our edge label, and then a few attributes, and then connect to n3. And now, finally, we have n2 connect n3. In this case, as you can see, since we don't really have any attributes here, we just don't need to include anything. We just label it with producers. Yep. Let me see. So we have this n1 connect. Yeah, I think here is here is n1 with n2 and n2 n3 and n2. I think here's a type. This one should be n2. Yeah. Thanks. And so actually, let me run this code actually to. I believe I already have the. If you can feel free to explore it on your own with this Neo4j sandbox. I use kind of like similar things. I just using this local client called Neo4j desktop. It should be the same. So here, I just paste in the create command here, and then I just hit enter. So it says, okay, we have 3 labels, create 3 nodes, and 9 properties and 3 relationships. Yeah, by the way, in the Neo4j terminology, relationships is just a synonym for the edge. So if we want to see, kind of like see exactly what the graph look like, so we use this command. So as you can see here, we have this Steve Carl, and we have a person as a label, its ID and the 2 attributes, and the office and the digital. So yeah, so here we kind of like being trying to practice and being ambitious and try to create an org chart of the paper company Dunder Mifflin from this TV show Office. So all edges will have the labels matches with I being numbers from 1 to n. The number of edges. N is number of edges, and here are some useful commands that you can use. For instance, the one I just showed is this match n return n, which basically you can think about this as select everything from the graph. And here we have limit 50, which means just return 50 nodes and edges. But in case the graph is really large. And these commands will have this match n, detach, delete n, which will help you to delete everything from basically your workspace. And to create a list of values, you can use this brackets. For instance, this row we can have sales assistant, the regional manager. So This suggests that in the attributes, the key-value pair, the value can be an array of a list of values. So you don't have to be a single key value, and value can be a list. Let's try to play around. We'll try to play around in case you have sign up for the Neo4j sandbox. You can start to play around with this graph. So maybe we don't really have a time for create everything, but here you can just maybe we can allocate like 3 minutes to play around with this how to try to create this graph. For instance, you can create this node and connect with an edge with another node, and then we can move on to the next material. So let's start, and then if you have any questions, let me know. Okay, so let me paste you the command. Actually, I already have made the command graph available here. So in case you want to play around, this is actually will create exactly the org chart that's shown in the slides. In case you can run the command in the sandbox, and later on we'll actually run some queries to demonstrate the feature of this Neo4j query language Cypher. So now let's take a little bit talk about more details about graph query language from conceptual level. So here we have so two important usage patterns for graph query languages. So one is called GraphPatternMatching, and the other called graph navigation. So these two patterns are widely concerned by everyone, no matter what kind of like syntax or language that you want to propose in graph for the graph database model. That specific language you propose kind of like need to support these two usage patterns, which are extremely important and widely used. So in this case, this time we only focus on the Cypher. However, any significant query languages will have these two important patterns in their languages. So let's first talk about graph pattern matching. So graph pattern matching, matching is the mapping from variables to constants, such that when the mapping is applied to the given pattern, the result is, roughly speaking, contained within the original graph. Someone may call it subgraph matching. So suppose we want to find, for example, we want to find the co-stars of the office. Again, we have this this office crew graph, and with the graph pattern for this query, actually find the co-star of the office actually can be visualized as follows. So we have this N2 TV show, we have this titled office, and we have two nodes. Two nodes here. One is called x1, which denotes as a variable we don't know. We want to match that variable to some nodes in the original graph. And the other node, we have this x2, again, another variable. And we have we have another constraint that whatever the nodes that we want to match by this x1 and x2, it has to connect to the TV show node via one via xin and the other also via xin. So that's how we model this co-stars of this query. So as we can see that actually the result actually is shown here. So so if we think about this, we can map x1 to Steve Carell and x2 to the BJ Novak. However, there should be another role here is that we flip. So we match x1 to BJ Novak and we match x2 to the Steve Carell. So this one actually is called result set, or in the graph database domain, it's called matching for Q1. So in Cypher, actually in the relational model, we talk about really the difference between set semantics and back semantics. We have similar things. Just the semantic difference among different query languages for the graph database model. So Cypher really has this no repeated edges and back semantics. So let's see. Let's see, for example, that we want to again the same query. Actually, let's take a closer look about how we can write such query in Neo4j. So this one actually, again the same query, want to find the co-stars of the office, and we have this visualization of the query that's a graph pattern that we want to match against the original office crew graph. So in the Cypher, we want to the syntax look something like this. We have this keyword match. We have this x1, which specify that we want to match. We want basically using this graph pattern matching to match against the graph in the workspace. And then we have this x1 person. Basically, we want to say it says that we want to match variable x1 to node with node label person. And now this x1 has to connect to the TV show node through an incoming edge with edge label x. And similarly, we have the x2 person, and then it has to have an edge that goes from x2 person to the office. So once we have basically this match pattern, we basically specify in the Cypher syntax specify this graph pattern using some syntax here, and then we just say we want to return x1, x2, which means we want to return the x1 and x2 here. So if you want to learn more, there's a Cypher manual online that you can see exactly what this the search term for this is called patterns. So let's see some examples. So here we want to actually query against the property graph we just created for this org chart of the underneath from the paper company. So the first query we want to run is called who's inside party planning committee, PPC. So PPC actually is a department here in our model. So the query actually looks something like this. So we want to match every node that has a label person, and we denote basically the P. The P is a variable that's corresponding to all the nodes that's with a label person. And then we have, again, the various exactly same, this where predicate saying that this party planning committee has to be in the P dot department. And then we want to return this P dot name. The second example we want to show is that how many people does Michael directly manage. So here we have this match P person manages. So basically here we want to specify a pattern. So we have first one we have this P variable. It has to match with every person. And then again we have another N variable here. It also has the same label person. And these two variables has to connect with since we are talking about directly managed, so basically we'll have one level down. So here we have this managers label on the edge. And then we return this n.name has to be equal to Michael Scott, and then we return count p, exactly count how many, basically how many values that this p combined to. So actually, let's run this example in our. Let me actually show this example and run the query to gain some sense about how basically Neo4j works here. So actually, the first thing we want to do here, actually, we already create a graph. We use this command here to delete this one. We can delete. Yeah. So once we have deleted this one, I think we can just paste in this graph here and then run. It should create a graph for us. And so once we have created the graph, we want to run the very first query here. We want to find out the person who's inside this party planning committee. So here we have this one, we set query, and then we get all the persons. So we have Angela Martin, Pam Beasley, Meredith Palmer, Kelly Kapoor, and Phyllis Lapid. So exactly kind of like if you actually look at the org charts, it shows exactly the same group of person that they are in the party planning committee. So now let's run the second query here. So there should be 8 people that directly managed by Michael Scott. Okay, so let's continue. So so next we want to basically find out kind of like different. I'll run a few more queries here. So first one is we want to find all the employees that are directly managed by someone that reports to Michael. And the second query we want to run is that does Michael directly manage more employees than Jim Halbert? Maybe here we can take 1 minute to think about what's if you want what you can write to express those two queries in Cypher syntax, and then we'll talk about in 1 minute. Okay, so anyone have any suggestions or what's your thoughts? Feel free to feel free to unmute yourself and say anything. So here we actually have this query about find all the employees that are directly managed by someone that reports to Michael. So it's a little bit complicated than the example we saw earlier. So here is actually the graph look like. So in the previous, we say, okay, we want to have one type of person node. We want to match against person node and then manage with another person node. Here, we kind of like do two levels matching here. This two level, I mean this two level when you do this, depth first search, you traverse this layer and by layer through this org chart. So first we have this match P, and we want to specify it has to, in this example we show that you can not only just match against the label of a node, you can also match against the attributes. So here we have a match P. It has to have the attributes name and Michael Scott. And then we have one edge that has a label called manages, and it goes to, like here is we're just using parentheses saying that it has to be some node. We don't really care because it's not really our focus here. And then such node, whatever that node is, has to have another edge called manages that goes to a node that with a variable q. So since we know that in the org chart they are all people, so essentially we don't really have to specify the label has to be person, but we can do that. We can do so here. So here we have this P has to be Michael Scott manages some person, and that some person has to manage Q, and we want to know that Q.name. So the second one is that's Michael directly manage more employees than Jim Halbert. So here's actually a little bit. This query is a little bit more complicated. So so here we're actually using two match. You can think about this as a match block. We use two match block here. We have match, first one P person, manages another person N, and then we have to have N.name equal to Michael Scott, and with count P as C1. So here is that we want to basically match every person that's, here I just illustrate another way that you can basically specify the same thing here, that here we say that P has to have this attribute name Michael Scott, but here we don't really, we don't say this name Michael Scott here. We're using this where predicate. So we say N.name has to equal to Michael Scott. And then we count how many persons are managed by Michael Scott. And then we use another match block that has, P person manages M person, and M person has to be Jim Halbert. And then we return this C1 and whether that is greater than count P. So one thing to note here is that each this match where can be solved as a select from where in the SQL query. So here is really a building block for the graph query language. It's really pretty much similar to relational SQL query. So we have this very building block is select from where, and we can just combine or doing different things with it. So here is this example. Actually, I want to show that we have a little bit semantics about this Cypher query here. So here we have this match where we have this Michael Scott, which is a match block here. And then we have another match block. This we want to match this M.name with Daryl Philbin, and we return P.name, Q.name. Actually, this query does is just it's actually doing a cross product, between this P, the rows or the values corresponding to P, cross product or Cartesian product with this values in Q. And you can run this query later on to see the difference. So the second actually very important pattern that any kind of like significant graph query language has to support is called graph navigation. So it's a mechanism provided by graph query languages to navigate the topology of the data. So previously, we want to kind of like, you can think about the graph pattern matching is that you want to extract some patterns from the target graph. And now the graph language has to offer some mechanism allow you to traverse the graph data that resides in your workspace. So there are, inside this graph navigation kind of like usage, we have two important query classes. One is called PathQuery, and the other called PathQuery plus GraphPatternMatching. Someone may call it navigational graph pattern. So they look very extremely similar, with a slightly difference. So let's take a look at this PathQuery. So previously, we basically using this match block, we specify a subgraph pattern, and we want to match against a given graph. Now we kind of like using the kind of like similar syntax. We match against we specify a path pattern, which we want to match against the graph. So here the path query has a general form of this P that from x goes to y with some alpha. Alpha specifies conditions on the passes that we wish to retrieve, and x and y are the endpoints of the path. So this alpha actually often represented using regular expressions or some form similar, very similar to that. So again, we have our old friend, this office crew graph we saw earlier plenty of times. And then we want to, again, we have this same query. We want to find co-stars of the office. So conceptually, we can think about this as we want to find two endpoints, x and y, and we have one edge called x in, and then we use this dots concatenates a symbol that's with another edges that x in, and here we have this minus sign. This minus sign here really represents, kind of like indicates that edge has directions. So you can see that actually, by the way, in the Cypher, in the Neo4j, there's really no notion of undirected edges. So every edge will have a direction. It's just like when you query it, you can specify whether to ignore the direction or not. So again, here we have this. We just express the same query actually using this path query pattern. So here actually, it's not really different much. So we have this kind of like pattern, this p x in TV show, and then x in person. But the only difference here is that we have this path equal to something, and then we return such path. So basically, we bind this query results, and we bind them into this path variable. So it's really nothing new here. But instead of return some variables p or q, here we return a path. So basically, here in this case, we want to say the co-stars really we have one path that goes from left to right, and then we have another path that goes from right to right. And the results look something like this. As you can see that by staring at this kind of like result, you can tell how you can navigate through the graph to find two such paths. This navigation graph pattern in Cypher is really combines this path query with graph pattern matching by allowing edge labels in the graph pattern to be paths. So in the previous let's see an example. So for example, we have this query Q2. We want to find all the people that Michael Scott manages. And actually, conceptually, this query actually looks something like the picture shown here. The only thing here we want to focus is this plus sign. This plus sign actually is if you are familiar with a regular expression, that means you want to return this edges has to appear one or more times in this pattern. So it gets translated into something like this. So this is actually kind of like things that you kind of like really had hard time to do in the SQL, that you have to write this recursive query. But here we kind of like relatively very easily to do in Cypher and Neo4j. Basically saying we are saying that we want to have the P person, that P has to be Michael Scott, and it has to match there's edges that goes through at least it shows up at least once, but it can show even like many times. So one or more, and then has to manage a person, a queue. So and then return all the queue name. So here, so let's see an example. So we want to find Dunder Mifflin employees that are on the same level as Michael Scott. So here so the query actually looks something like this. So here we have the first match block. We have this person, P, and then we have another person, N. We have this managers. Notice this star here. In the previous, we have this star 1 dot dot. That means that this managers has to show up, this edge has to show up at least once. But here, we really don't care. We can say, okay, maybe some person self-manage himself. So we don't really care whether this matches show up. It can show up 0 or more times here. So we have this first pass, we have P1, and then we have a second pass, P2. That's again the same person P, and then a different person N. So and then we require that the length of P1 has to equal to length of P2. And we cannot have M and N both map to the same person, and then N has to be Michael Scott, and then we return M. So let's see. Let's query the same data in the relational model. So here it's kind of like a snapshot or a part of the data that we model with the org chart in the relational model. We have this employee ID, name, role, department, and the manager ID. And as you can see, this one we have several constraints here. Is that basically your CFO doesn't really have manager, but for instance, this Ryan Howard serves as a VP of Northeast region. It has employee ID 2, and its manager is a CFO, David Wallace. So how we can express the same query, get the Dunder Mifflin employees on the same level as a Michael Scott. So here's what we do. It's exactly the kind of like recursive query that you expect to write. So here we have this base case. If two people are on the same level, their manager has to be the same. And then we have this recursion. It's the same idea as a base case, but use the base relation and the result table we just computed in the base case. So you can see that how different models, even though we can model the same data using the different models and using write the same kind of like query with different two languages, but one language definitely more intuitive than the other, which is shown here in the top right column. So let's practice a few queries. First one is that does Jim Halbert match Felix Lapin? So this one actually we want to see whether there's a path that goes from Jim Halbert to Felix Lapin. And then there's a second query called find all people that are indirectly matched by Michael Scott. So here, this is a query look like. So it's quite intuitive. We have again the same kind of like path pattern that we have a P and a Q, and P map to Jim Halbert and Q map to Felix Lapin. And we require that such path has to be greater than 0. So there should exist such path. Sorry, actually, the path, this one actually requires that the result set has to be greater than 0. There cannot be empty set. Okay, so here is that we want to have a path that goes from Michael Scott to whatever the person, and then the person has to be distinct, which is pretty straightforward. So here, a Cypher allows the uses of graph algorithms. So you can directly use graph algorithms in Cypher. So that's kind of like a very important feature for any graph query languages. For example, let's see this Q3. We want to find the shortest path between David Wallace and Andy Bernard. Actually, there's a built-in library in Cypher or Neo4j or any other graph database vendor that allows you to say directly invoke a procedure called shortest path, and then inside the argument for such function, we just specify this path pattern. We want to find basically the David Wallace, and it has to go through some edges, and it can reach Andy Bernard. And we want to return the shortest one among all the passes, and we return such path. So there are actually more graph algorithms like PageRank, centrality, connected component algorithm, etc. that you can directly use using the Cypher directly. You don't have to write your own query or figure out how to do that primitively inside Cypher. So since we already talked about about Cypher Query, so it's really important. So like what we did with relational model, we want to understand a Cypher Query, how it works. So Neo4j has a explain command, just exactly like the explain in any database vendor that you probably already used in your homework to try to understand the performance of a given set of queries. So for this section, we're actually using the following data as to kind of like illustrate how we can do similar things in Cypher and the Neo4j using Cypher. So here we have this 3 table R3, R2, R1, and we want to insert a bunch of values to R3 and R2 and R1. And the query we want to run is that this multi-way join query that selects from R1 natural join R2 and natural join R3. So we want to select everything from just join R1, R2, and R3. The result should be only 2 rows here. So the plan for the SQL query looks like this. You're probably already very familiar. Here I'm using this Postgres. It's really doing the merge sort between 2 relations, and then merge sort with a third relation and produce the merge join to produce the join result. So let's actually model the same data in property graph model. So the guidance for the guidelines to map any relational model to graph model is really quite simple. So we have so each row has to become a node, and the table name now becomes a label name, and the join or foreign key now is a relationship which just edge. So here is actually our first attempt. We want to create, we will create exactly the same data. The graph actually looks like this. So we create this N1, we have the same, as you can see, the R3 table, R3 table becomes the R3 label. So we have this R3 label, 1, 2, 3, we have 3 nodes because R3 table contains 3 rows. And the R2 table contains 4 rows, and so exactly we have 4 nodes here. And R1, and the R1 table contains 2 rows, so we have 2 nodes here. And then we create this match. So the match of this block can not only can be used as query. You can also use it when we actually want to add edges. Here we want to match R1 from R1 label and R2 from R2 label, and we want to create this R1 with an edge that connects with R2. So why this one is not really a correct attempt to create the data? So the problem is really coming from this part. So as you can see, recall that we want to, the guideline, the third point of guideline is that we want to create edges whenever there's a join or foreign key. But here, for example, we want to take a look at, say, for example, let's say this edge between this R3 node and this R2 node. This one has attribute A and with value B, and this one has attribute A and with value A. So these 2 nodes, if we want to do join, these two nodes cannot be connected. So they cannot be. So this essentially we are saying that in the relational model language, we are saying that these 2 rows cannot join together. So so to map that information in the property graph model, we cannot create an edge. It's not like we cannot, but it's a less against creating an edge that connects the two nodes that cannot join together. So in this case, essentially we are doing Cartesian product. As you can see, each node will connect every other node. A better attempt here is that we're adding where predicates. Here we have adding this where predicates r1.b equal to r2.b, and similarly we have this r2.a equal to r2.a. As you can see, the graph here is compared to the previous, we remove lots of edges. So now only that basically only the rows that can be joined are connected via direct edges in our property graph model. So resulting graph in Neo4j will look something like this, different color, which basically indicates different labels, the nodes with different labels. So there are really two observations we can have. Is that one already mentioned in the past, that Neo4j doesn't really have a notion of undirected edges during the graph creation. User can ignore directions when they query the graph. So in other words, we cannot create undirected edges. Or you can by basically doing one direction and the other actually goes reverse. But we can just create one edges, and when we query the graph, we just ignore the directions. And another thing is that unlike relational model, part of the join computation is already done during the graph model creation. So when we actually create these edges, we're kind of like already saying that, okay, only these two nodes can join together, but these two nodes cannot be joined because we don't really have edge that connects these two. So recall our example of SQL query. We have this select from R1, natural join R2, natural join R3. To express the same query actually inside Cypher, this is actually our first attempt. We can directly translate that SQL query into a Cypher query. So we match every node R1 with label R1, R2 with label R2, and then R3 with label R3. And then we have this where R1.b equal to R2.b and R2.a equal to R3.a. And then we return the join result. As you can see, this select from where, kind of like a building block, matches exactly like this match where and return. So let's see how good that query is. So by checking its query plan. So as you probably already expected, so in the Cypher we just attach this explain keyword ahead of our query, and then we'll get the query plan. The query plan actually for the query above actually looks like this. So here is the three-way join. It's computed using hash join in a pipeline fashion in Neo4j 4.2 optimizer. So here we have a node by label scan. You can think about this as a table scan in the relational physical operator. And then for Neo4j doing some caching when you create a graph, you can just ignore it when you read the plan. So we have this node scan, and then we have a node scan where you scan. So basically we do node scan, and then we do value hash join, essentially hash join between R1 and R2. And then we do node scan again on the R3, and then we do hash join between this R1 join R2 result and R3. And then we do projection, then we do projection, and then we basically produce a join result. However, actually this query is not so good, because if you actually run this query inside Neo4j, you will get this warning. So the warning says that this query builds a Cartesian product between disconnected patterns. So essentially, the problem is that we try to use Neo4j exactly like what we do with relational database management system. So that kind of like suggests that the above Cypher query is really anti-pattern. So it's like we can write it inside the Neo4j. There's no problem there. We can pass a syntax check and a semantic check. It's not the right way to write such query. So recall in homework 4, we saw the semantics of semi-join graph. So A semi-join B really means that giving us a set of starting vertices in B returns a set of vertices in A that connected to those starting vertices via edges. So this kind of suggests that a multi-way join query is really a graph pattern matching query. We can build these connections between two data model world. So the corresponding Cypher query, we can actually write something like this. So we have this R3 has to connect with R2 via edge, and then R2 will connect with via different, again, edge will connect to R1. And then we add this where predicate, this R2.a equal to R3.a and R2.b equal to R1.b, and then we return something. Now, actually, if we run exactly the explain command, we will get actually a quite different plan. So here is that, let's take a look at this plan. So we have this, again, the node scan. You can think about this as a table scan. So we basically find all the nodes with this R1 has to have this capital R1 label. And then we use this expand all. So what does this expand all does is that, like, it's given a start node, and depending on the pattern relationship, the expand all operator will traverse incoming or outgoing relationships. So in other words, is that you can think about this as, if you think about this as a breadth first search, we first want to select one node, for instance, this R1 node, and then we do this one level breadth first search. We're following the edges that goes out from such node, and then we return all the nodes that's on the same level that connected to the given node, that connect to the starting node. So here, actually, we can see that this expand all from the plan, that is expand all plus this filter is really works like a join. So let's take a look at this one. So, suppose like with the execution starts with lowercase r1, and then we follow the edges that goes from r1 by one more level to find all the r2s that satisfy these conditions. And then the filter applies that with predicate this r2.b equal to r1.b. So if you think about this as using semi-join or like a join, you basically join two tables together, and then you apply this filter predicate. So recall that each match where can start as a select from where. So here is this one is another way to write the same query, and also with exactly the same plan like here, but with different syntax. So here we have match, that is R2 match with R3 first, and then we have the predicate, and we denote the result. So basically, we are saying the old R2 that satisfies these patterns, we save that, bind that to the variable R2, and then we use exactly the same variable in our second match block here, and we have another edge that goes to R1, and we attach additional where predicates, and then we return the result. So here we kind of like simulate this plan by doing this kind of like a level by level traverse. So one lesson actually we learned from here is that actually essentially we are trying to express the same query. We just simply using the different syntax, but the query plan can be very much different. If a Cypher Neo4j optimizer can have a very good or sophisticated optimization logic, it should identify that actually our two queries are essentially the same, and they should produce the exact same plan, but which is not true here. So actually, the last we actually take a look at a real case study that's a term project done by a student actually in the same class in spring 2019. So the project he does is that trying to run some queries against a large collection of data. So his data, if modeled in relational model, it roughly around like 2.2 million rows. And the example query he wants to run is that, for instance, where are all my photos inside such huge collections of data? So if you can think about this more concretely, such scenario is more like query against files stored in S3 buckets, or query against log files collected over time from different services on AWS. The idea there is that he modeled the data in relational model that run on Postgres 11, and then the corresponding graph model in Neo4j 3.5 and compare the performance. So, but despite the models that used in the project, the raw data really about trying to the raw data is really a graph, labeled directly a graph, but we simply model the data in different data model. So one query he runs is that it's called exact file name match. Basically, return full paths of files that match a given file name. Here, actually, this one is directly taken from his report. So here is a recursion SQL as we expected, which has something form like that. Actually, this is exactly the same query that serves the exact same purpose, but actually run right inside Cypher. The takeaway is that actually the Cypher query is much shorter than the SQL counterpart. So on average, in the report, there's basically Cypher is less than 1/3 with its corresponding SQL query. But similar study, newer and similar studies show that there can be even greater reduction. So occasionally, you can see that Cypher query only less than 1/10 in terms of lines of code compared to the SQL query. So that really suggests, we can have easier development and code maintenance. Here is the benchmark that's takes from his report. So one thing to notice that on this entry is that we want to find, for instance, the query is that find all txt files, and we have this ordered limit 1000, and Neo4j runs like around 600 milliseconds, and Postgres can run 56 milliseconds. So even though we talk about lots of graph databases, but in terms of maturity, about how fast the query can be run, a same query can be run in graph database model, in graph database and the relational database, it's just Postgres can still outperform Neo4j for certain queries. The second one is that the report doing lots of hand tuning about Cypher query in order to speed up the performance. So for example, he wants to find all the txt files. Here he used different kind of syntax, using its root label and using with keyword and using where predicate. Actually, Neo4j gives very different runtimes to execute the exactly same query. So what this suggests is that Cypher query still needs many hand tuning, but hand tuning basically means that the human, the user, doing the optimizer job, writing query in different ways and overriding Neo4j Cypher query optimizer's choice of query plans and trying to search for the best plan that gives the least runtime. So that's kind of suggest that Cypher query still needs many hand tuning to reach acceptable performance, and that really means Neo4j optimizer still have a huge room for improvement if we take a look at this. So in conclusion, in this class we kind of introduce two graph models. So we first introduce edge label graph, and then we introduce property graph, and we also introduce different kind of graph query languages: SPARQL, Gremlin, and Cypher. And then we introduce kind of three important query usage pattern: GraphPatternMatching, PathQuery, and NavigationalGraphPatternMatching. And we demonstrate and practice those usage patterns in Cypher with Neo4j. And we kind of using one query to show that how we can use explain command to profiling Cypher query in order to identify the performance improvement, possible performance improvement. And lastly, we see a real-world use case study on relational model versus the graph model. And we see that graph query is essentially much easier to write and maintain. But in terms of query performance, Neo4j still have a long way to go to build a sophisticated optimizer, just like Postgres. Okay, so Moving forward, so I will upload all the slides and the codes to the box for the reshare. Thanks for everyone.